right, hopefully that's working now. Right, we're recording. So, nonlinear transformation. So we're going to start off talking about these things called derivative matrices, particularly their use in something called the affine approximation. Okay, so if a function going from Rn to Rm, please keep quiet, is not linear, then it cannot, in its entirety, be represented by a matrix. Okay, all right. Suppose that a function that we're going to be calling capital F going from R2 to R2, nice and simple. You plug in a 2D vector and you get out a 2D vector. I think a shuttle must have just arrived, judging by the influx. Is of the form big F of xy. Okay, so here we have our function. So the components of big F are component functions, where our input to our function will be a two-dimensional vector and our output also will be. Where both little f and little g have Taylor expansions. I'll talk about that. About the point AB. Okay, so let me just give you a little bit of a rundown on Taylor expansions, or Taylor series, Taylor polynomials. And we'll be talking about these more later on in the course as well, but just for now, a Taylor polynomial, a Taylor expansion, they've got various names, are approximations to functions, where you have a function that is typically not a polynomial, but you approximate it with a polynomial. So a linear function, which when you draw it would be a straight line, is a polynomial. It's a very simple polynomial. So if you have some curvy curve, and you take some point and you draw its tangent line at that point, you could say that the equation of that tangent line is a first degree polynomial approximation to your curve. Where very close to the point is actually not a bad approximation, but of course you don't have to get very far away from the point before it becomes a pretty lousy approximation. What you can do is you can add another term and actually have a quadratic representation of your approximation of your function. So basically, instead of approximating your function with a straight line, you'd approximate it with a parabola. And that, of course, has the capacity to be a slightly better approximation, because not only can it match the original function in both function value and slope, but it could also match it in concavity at that point. And then, of course, the further away you get from that point of tangency, the worse the approximation typically becomes. And so Taylor expansions, you can keep adding more and more and more higher degree terms and make your polynomial approximation a better and better approximation. So you can approximate your function with a cubic, or with a quartic, or with a quintic, and going up and up and up in degrees in polynomials. And that's Taylor expansions. And with Taylor expansions, what we usually say is we usually put a plus dot dot dot, and we assume that it goes on forever with higher and higher and higher order terms. Taylor expansions are really nice because polynomials are very easy to deal with, because polynomials fundamentally just come down to multiplying and dividing. So whereas your original function might involve exponentials or trig functions or log functions that are tricky to do calculations with, numerical back-of-the-envelope calculations with, pen and pencil calculations with, polynomials are actually very easy. So Taylor expansions are quite useful and powerful things. There's some little hidden terms and conditions, because sometimes there's a limit to just how well you can approximate your function with a polynomial. Think of a function that has a kink in it. Polynomials don't have kinks. It's impossible to build a kink into a polynomial. So if you're trying to approximate a function close to a kink or at a kink, there's a limit to how well you're going to be able to do it, because and then the more and more terms you add, you can sometimes, if you graph it, you can get some rather crazy looking functions that have these strange spikes in unexpected areas as the function tries really hard to approximate something that it just can't. But Taylor approximations on the whole are very powerful and are very effective tools for dealing with functions. Okay, so little f and little g could be anything. Our supposition here is that little f and little g do have Taylor expansions. We can approximate them by polynomials. Okay. So where am I going after this? Okay, for the conversation today that we're having, we're interested in only the first degree approximation. So in a sense, like a tangent line. Okay, I've got a little note here. I'll give you the note. Taylor expansion. A polynomial approximation. Here, today, we are interested in the expansion up to first degree terms. That is the linear approximation. Because what we're going to be doing is we're going to be approximating a nonlinear transformation with a linear transformation. Okay. For a single variable function, the linear approximation is essentially, if you drew it, would look like a tangent line. For a two variable function, it would be a tangent plane. For a single variable function, this is equivalent to the tangent line. For a two variable function, it is equivalent to a tangent plane. Okay, all right. And we're assuming this little f and little g, the way we've set up our little theoretical situation here, we have to find f and g as functions of two variables. So if, let's talk about little f first. If this function, z equals f of xy, is a differentiable function, which it would have to be to have a Taylor expansion, then the tangent plane at AB is, okay, so first I'm going to write it in the familiar form, which we've already seen earlier in the course. Okay, tangent plane equation. Z minus Z naught is the x derivative at AB times x minus A plus the y derivative at AB times y minus B. Or we can write it in a slightly different way, and the slightly different way would be the Taylor approximation way. That's just how you write Taylor series. Instead of z, I'm writing f of xy. Instead of z naught, I'm writing f of ab. Yeah, z naught. I'm mixing up my notation in that previous line. Oh, well, it doesn't matter. And that's what a Taylor expansion looks like. In fact, if you want to look a little bit into the future, you can look at page 73. And if you look at the box at the top of page 73, you'll see a function that looks a lot like what I've just written, but with some more terms in it. And that is that formula there in the box on page 73 is the Taylor expansion of a two-variable function up to second-degree terms. But today we're stopping at first-degree terms. Okay, all right. Yes?
If you're doing first degree and you do this, does that mean that your fx, y will only its highest degree will be what? Of the answer? Was that like
Yeah. Yeah, well then it means that you're making a fairly poor approximation to it. Yeah. So yes, this approximation will only go up to x to the power 1 or y to the power 1, linear approximation, which will probably be quite a good approximation to your function, very close to the point, but you won't have to go particularly far away before it becomes not a very good approximation anymore. And just to keep everybody in view of what the journey is that we're on here, what we're aiming towards is looking at coordinate changes in integration, specifically what happens to the little delta A and delta V when you do a coordinate change. And delta A's and delta V's are very, very small. So the entire context of this is that we are looking at things that are very, very small. We're not actually going to be moving very far away from points of tangency. And so the approximations that we'll be making are acceptable because we're dealing with very small things. Okay, that it's hard to see that sort of destination at the end of the journey when we're dealing with all of this stuff over here, but that is where we're going. Okay, all right, affine approximation. All right, derivative matrices, right. I'm just looking at my notes here, and I've made a little bit of a notation change. I can't remember why, possibly just for to make what I'm writing a little less chunky. Instead of x minus a every time, I'm going to be writing h, and instead of y minus b every time, I'm going to be writing k. This does mean that x becomes a plus h, or at least I can choose to write x as a plus h, and y I can choose to write as b plus k. Okay. We can now write this thing over here. I'm going to change slightly. I'm going to write it as f of a plus h, b plus k equals f of ab plus h times f of xab plus k f of yab. I'm simply rewriting that previous line, slightly more compact. Okay, so here comes some important stuff. If h and k are very small, and we will only be dealing with very small things, we can say that. All right, well, the first line is simply rewriting my big F. I'm choosing to write it as a column vector because it'll make it easier to write on the page. If I write it as a row, if I write little f comma little g, little f is about to get quite big and little g is about to get quite big. So if I were writing it horizontally, I'd be forced to flow over into two lines and it would be a bit awkward. So I'm choosing to write it vertically, but that's just a style choice. Equal. So now I'm going to replace f of xy with that thing that I called star near the top of the screen. If I were choosing to replace it with its entire Taylor polynomial, I would write something like this. HOT, that's not hot, that's higher order terms. And what I've done is I've kept the equal sign as a true equal sign, because the idea behind polynomials, is Taylor polynomials, is that if you just allow the number of terms to go off to infinity, your approximation is actually a true representation of your function. Terms and conditions apply. You get things like called the radius of convergence, where in fact that statement's only true within a certain interval. There's stuff. There's Taylor polynomials has its complications and its various conditions, and you can say here's the statement of Taylor's theorem, and then you're always able to come up with exceptions like kinks and things. But on the whole, that's the idea. But now what I'm going to do is I'm actually going to replace the equal sign with a wiggly equal sign. Question?
What is that f of x, y is equal to? Is that a real change?
It's my function, which I'm just choosing to write as a column vector rather than as a typical horizontal vector, as a row vector, simply because it's going to save space on my page. So it's, as I say, it's kind of a style choice to write it that way. I could have written all of that F stuff plus HOT and then comma, and then have written all of that, but I knew that that would involve a rollover into the next slide, so I'm choosing to write it. So it's a style thing. I'm just choosing to write it this way. So the thing is that capital F is a function, but capital F's output is a vector. I mean, when you put in a vector, you're going to get out a vector. So you can choose to use vector notation and write it as a column vector instead of a row vector. Because fundamentally, capital F is a vector. It's just a complicated looking vector full of x's and y's. Okay, now what I'm going to do is I'm going to write that star thing and I'm going to drop the higher order terms. But that means that I have to draw a wiggly equal sign because it's no longer truly equal. It's an approximation. Okay, so this stuff that I'm writing here is the Taylor polynomial, the Taylor approximation to little f and little g up to first degree terms. Okay, I'm at the bottom of my page, so I must just be careful to save space. What I'm going to do now is I'm going to split this up. The f of AB, g of AB, I'm going to put in a standalone vector of its own. Plus, now I've got two terms left at the top and two terms left at the bottom, but h appears twice and k appears twice, and what I really have here is I have a matrix product. Okay, so take a little moment to read what I've just written and agree that what I've written is true. Unless I've made a silly mistake, what I have written is true. So if you take that matrix and you multiply it by that vector, you will get those four terms, the last two terms, top and bottom. And then you add that, so if you do this product, you'll end up with a vector that has two components at the top, with an h and a k each, and two components at the bottom. It's still a vector. I shouldn't say components, terms. The first component will have two terms, the second component will have two terms, hk, and then when you add it to this, you end up with that thing over there. Okay, I hope you agree that that is true. And then what we usually choose, that first vector, of course, is just simply capital F evaluated at AB. Plus, I'm going to leave that vector hk written as hk, but that matrix there, I'm going to give a special name to, and I'm going to call it capital F dash, and that thing over there is called the derivative matrix. The derivative, sorry, I'm right at the bottom of my virtual page. So it's a bit squashed. The derivative matrix of f at, let me move my little thing out the way, at AB, and that's that. Okay, so big F is effectively a vector field. You have input vector, you have output vector. So capital F dash is the derivative of big F, but the derivative of big F is a matrix, which is the first time we've seen such an animal. But the derivative of big F is a matrix. Suppose it's not quite the first time, because we've seen grad. Grad of little f would be a vector, but it didn't use the dash symbol. And we're used to that dash symbol being quite a simple little thing. Back in first year, if you had little f and little f dash, you wouldn't have either vectors or matrices making an appearance. But here, big F dash, matrix. It's called the derivative matrix. And everybody happy? I'm going to do a page jump. It's fine, I'll scroll back. There's no way to do a gradual page jump here. It just gives you next page. There you go. I'm going to do an example. just finding derivative matrices. Let's just practice finding derivative matrices. I'm going to do exercise 80. Find the derivative matrices of the following transformations. Well, the first transformation is actually a linear transformation. The derivative matrix of the given transformation is 1, 1, 3, minus 1. Now look at that. That, a few days ago, we would have been saying that is the matrix that represents the linear transformation. Writing the linear transformation in a function way is the top. That's function notation. But we could also describe the action of that function in a matrix product, and that would have been the matrix. And I didn't at the time use the term derivative matrix, but that's what it was. However, as soon as our transformation stops being linear, our derivative matrix suddenly gets variables in it, which in a linear transformation is not the case. So B has f of x, and what is it? It's x squared plus y, oops, in brackets in funny places here, x minus y cubed, f dash, what's f dash going to look like? It's going to look like 2x, 1, 1, minus 3y squared. Okay, the derivative matrix. The top row represents the two derivatives of the first component, the x derivative and the y derivative. And then the second row gives displays the two derivatives of the second component, the x derivative and the y derivative. Easy, right? Let me do a few and then you can have a turn. Sine x, cos of xy. What does g dash look like? G dash looks like cos x 0. Differentiate cos xy with respect to x. It'll be minus sine xy times by y. So minus y sine xy. And that'll be minus x sine xy. Yes?
How come in the linear one we leave out the variables, but in the other one we don't?
But there are no variables because the derivative of x plus y with respect to x is just 1. And the derivative, so that is a phenomenon of linear transformations, that the derivative matrix of a linear transformation has no variables in it. Because every time you differentiate, the variables just all go away. It's part of the linearity identity. And then D, what's D? I don't think you need to see me do any more. You've already got the hang of it, but let me do a few more. X squared y, y squared, xz squared. So here, big M is being written as a column vector. Doesn't have to be. Could have been written like the two above. Simply a style choice. Big M dash. Well, let's have a look. There are 3 components, so they're going to be 3 rows. And there are 3 variables, so they're going to be 3 columns. So here we go, 3 by 3. What do we got? We've got 2xy, we've got x squared, we've got 0, we've got 0, we've got 2y, we've got 0, we've got xz squared, 0, 2xz. Okay, each component of your original function corresponds with a row of your derivative matrix. And each column in your derivative matrix corresponds to derivative with respect to a particular variable. So that one goes with there, that goes there, and that goes there. And this one is all about d by dx, and this one is all about d by dy, and this one is all about d by dz. Okay, very ordered, very ordered. By the position of any one component of that matrix, you'll know exactly where it came from and what it's representing. Was there a question? No. Okay. I've got 2 more to do in my little 80 here. A of x, y, z. You can see I was running out of names when I was typing this up. X, y, y plus z, z squared. Oh, that's a nice easy one. Is it? Yes, it is. It's also 3 components. also 3 variables. So once again will be 3 by 3. Y x 0 0 1 1 0 0 2 z. And next one's quite fun. Next one's going to be an asymmetric matrix, because W only has 2 components, so the derivative matrix will just have 2 rows, but it has 3 variables, so they're going to be 3 columns. Let's have a look. There'll be e to the y, there'll be x e to the y, and there'll be 0, then there'll be 0 0 1 over z. Okay, you give it a go. Try 81. I'll just write here, you try 81, and then I'll scroll up. Up, up, up. Alrighty then, let's move on. So this formula that we've just seen, this f of xy is approximately equal to f of ab plus f dash of ab, and I had hk, I'm writing here x minus a, y minus b. When it's written like that, we call it the affine approximation. This is the affine approximation to f at ab. We can go through the same process that we went through before with Taylor series with 3 components, and we can extend, I don't want to write the word extend twice. We can extend this expression or formula or idea to 3 dimensions, where capital F of x, y, z is approximately equal to capital F of ABC plus f dash at ABC times x minus a, y minus b, z minus c. Okay. In fact, I think it's even in a box. Yes, it is. It's in a box. It's in the box on page 53. So just to put this in the context of things that we already know, I'm at the bottom of another page. Ooh, this is going to be a 3-page lecture. That's quite a lot. A differentiable single variable function can be drawn as a curve and its linearization at a point is its tangent line. Okay, page jump, but don't worry, I'll scroll back. That's fine, everything's fine, everything's fine. Just keep breathing, there we go. Thank you for the obligatory sound of alarm. It's part of the process. A differentiable 2-variable function can be drawn as a surface and its linearization at a point is its tangent plane at that point. Okay. So what about this animal that we're currently dealing with? A function which has vector input and vector output, like this capital F story, is called a vector field. Am I scrolling too fast? That big gap doesn't help, does it? It's called a vector field, it cannot be drawn as a single object, like a curve or a surface. Okay, I will carry on. So I'll say what I'm going to write. It cannot be drawn as a single. I've written single structure here in my notes. If you want to draw a vector field, the best way to draw it is with a direction field. Basically, on a grid or on some sort of array, you draw lots of little arrows, where the length of obviously the direction of the arrow is informative, and then the length of the arrow represents the magnitude, and you can then see sort of flow in your direction field. But they're tricky things to draw. So curves are easy to draw. Surfaces are a little bit trickier, but still they're not too bad to draw. But vector fields are not easy to draw. However, they can still be linearized. And the linearization of a vector field is called its affine approximation. But it basically plays the same role as a tangent line or a tangent plane. It's just not as easy to visualize in a picture. Okay, it cannot be drawn as a single structure or single object, but it can still be linearized its linearization at a point is its affine approximation. And I hope when you look at that formula for the affine approximation, you can see a family resemblance to straight line equations. Y equals y, that y minus y naught equals mx minus x naught, that sort of formula. There's a family resemblance there. Okay, just like any linearization of a nonlinear function, just like any linearization of a nonlinear function, it can be used as an approximation for the function where the approximation is a good one as long as we don't move too far away from the point. As long as we don't move too far away from that AB, that point of tangency, as it were. As we do not move too far from, I'm writing the point of tangency in inverted commas here, because it's hard to think of that AB as a point of tangency, but it's the same idea as in straight lines. Okay, I realize according to the clock here we only have 3 minutes left. But I'm going to fairly rapidly do an example, number 82, because we are almost a lecture behind, because I spent too much time on linear transformations last week. But it's just plugging into a formula. It's not a hard thing. So exercise 82 says, let capital F be x, y, z, x, y squared, y, z. Use the affine approximation to big F at the point 1, 2, 3. So I'm interested in the point 1, 2, 3. To find the approximate value of this other point, of f at this other point that's fairly close. So first of all, we have to build up the affine approximation. So we know that f of x, y, z, yes, it's a 3D one, is f of ABC, oops, plus f dash evaluated at ABC times x minus a, y minus b, z minus c. So we've got to work out all of these things. So f at ABC is very easy to work out. That's just f at 1, 2, 3. And we'll work that out. And we get 6, 4, 6. Okay. We need to work out what our f dash is, what our derivative matrix is. Okay, we've just done a bunch of those. They're easy. That'll be y, z, that'll be x, z, that'll be x, y. That'll be y squared, that'll be 2xy, that'll be 0, 0, z, y. There we go, there's my derivative matrix. And I need to evaluate that derivative matrix at 1, 2, 3. F dash at 1, 2, 3 is, when you plug it all in, I actually am just copying from my notes here, but it's simply substitution. 0, 3, 2. I've made a little note in my scribbles here. Oh, no, that's fine. Okay, what's left? Well, for the affine approximations, nothing is left. I can now write down my affine approximation for big F. My affine approximation for big F is the vector 6, 4, 6 plus the matrix 6, 3, 2, 4, 4, 0, 0, 3, 2 multiplied by x minus a, but a, b, c is 1, 2, 3, remember? Okay, that is the affine approximation. And that's essentially, that is like a straight line equation. It plays the same role in a vector field as a tangent line does in a single variable function. Okay, but then the question did say that we should use our affine approximation to approximate big F at this other point. So all you do is you plug that other point into x, y, z to, no, 1.1, 1.1, 2.1, 2.9, and you simply plug that in where x, y, and z were. 1.1 minus 1, 2.1 minus 2, 2.9 minus 3, ta-da, and then you just multiply that out. So you multiply the matrix with the vector and get something with some little decimals in it. Add it to 646. Okay, I'm not going to scroll any further. I will complete these notes, but I'm currently writing and scrolling too fast, so I'm just going to pause there. There are 2 more lines to go. The one involving some multiplying out and then the final answer. I will complete those, but you can see what to do from now on. First thing tomorrow morning, I'm going to ask you to do number 83 and basically practice doing the same thing. Question? How you do a 3 by 3 product. So you take a row. Take a row of the thing on the left and a column. There is only one column of the thing on the right, and you do essentially a dot product between them. So you'll do 6 times 0.1 plus 3 times 0.1 plus 2 times negative 0.1, and you'll get a number, and that'll be component 1 in your vector that you are creating, etc. So you take the rows one by one and essentially dot them with that column. Oh yeah, registers. Thank you. Thank you. There are registers floating about. Please do sign them. And there's a pencil case.